Yeah, let me just if I could say a couple things. I just want to welcome everyone to the SMART webinar today. We're very fortunate to have with us Paul Johnson from Los Alamos National Laboratory. He's doing some really groundbreaking work applying machine learning to different signals from the subsurface, and he's going to talk to us today about some of that work. Thanks, Paul.
Thanks, Grant.
Go ahead.
So, hi everybody. Apologies for the technical difficulties. Anyway, let's move ahead, and we'll be sure to finish on time. So the intent here is to show you sort of a vignette of some really interesting work regarding teasing out signal that we thought was noise that turns out to be really important to understand the physics of the system, and then to tie the work to other work going on at our institution and others. So with that, I'll go ahead. Raj, can we go to the next slide, please? So just the contents. So first, I want to kind of address the sort of new way of thinking that machine learning, when we incorporate machine learning into our work, sort of the new construct in terms of the way we have to address these problems. Then I want to give you an example problem. This is fault slip in the laboratory and Earth. Then I want to talk about, as I mentioned, some other topics, assuming we have time at the end, that are all related to this topic, and topics almost all of us are working on that are online here. Next. So can we go to the next slide, please, Raj?
Oh, sorry. Here you go.
Okay, so here's sort of the basic question that we're posing for the vignette I mentioned regarding teasing out information from signals that appear to be noise. And in this case, it's seismic data. So typically when we look at seismic signals, we catalog data that contain a compressional wave, shear wave, surface wave, etc. And we use that information, that catalog data, to probe an earthquake source. We use that for imaging and other applications as well. The question we're asking is, what about the information contained in the signal that looks like noise preceding that signal that you've recorded and following it? And so over the next portion of the talk, I want to address that issue. Next slide, please. So again, typically in the classical approach, we have a hypothesis. In this case, we hypothesize that the continuous seismic signal contains information regarding the instantaneous slip and future behavior. Next, please. We apply familiar analysis approaches to test the hypothesis. Next. And there is no link, so we determine the continuous signal is mostly noise. So this is exactly the procedure we went through. Now, in applying a machine learning approach, in this case specifically a supervised learning machine approach, I want to remind those of you who are familiar with machine learning and those of you who are not familiar, I want to walk you through this. But in this specific instance, we take the seismic signal we're recording and we try to map. We pose the question, is there information contained in that signal regarding the fault properties at any given time, and specifically slip or shear stress on the fault? And so we extract a feature space from that signal. These are statistical features taken out of the signal, and we actually try to map those features to the fault properties in this case. And that mapping is the machine learning model. And that model is something that is built sort of automatically. We pick a certain technique, maybe neural networks, it may be decision trees, whatever, and the model is built. We test that, and then we apply that. So we're going to go ahead and do that over the next portion of the talk. Next, please. So again, I want to reemphasize the hypothesis that continuous seismic signals contain information regarding the instantaneous slip and perhaps future behavior of the fault. Next. So we develop. So we start with the input data, as I pointed out, and the label is, in this case, the fault displacement. Next. We developed a feature space with some intuition, but allow many features we deem unimportant to remain. Next. We build a machine learning model. Next. We train the model on part of the continuous data. Next. There's generally a validation step before we actually test the model. And then we test the model, and then next. Next, we identify the features linking the input to the label. And after that, we tease out the physics of the features, which is really our goal here. So we're applying this new set of tools to try to tease out not new, but physics that may be hidden within the signals we're looking at. Next, please. So here are actual data from a laboratory experiment that we conducted in Chris Marone's lab at Penn State. On the left, you see the shear experiment. So it's a biaxial experiment where you apply a horizontal load to hold the system in place. You push that central block down at a constant velocity. There's gouge material contained between the three blocks. You measure many things, including the mechanical data from the system, and that includes the shear stress, the friction, the displacement, the layer thickness, etc. But you're also measuring the seismic signal coming out of the system, or the acoustic emission, as you wish. But it's a continuous signal that we're talking about. So in the right-hand figure, what you see are recorded data. And focus your attention to that central signal, which is strain versus time. That's actually dynamic strain. That's just amplitude versus time of the continuous acoustic emission. The upper signal is the shear stress on the fault measured by the system itself. You can see there's an earthquake, and associated with that is a burst of acoustic emission. And there's a buildup in the shear stress over time. You reach an instability, and then there's another earthquake in the laboratory. So you're seeing two earthquakes here and a burst of acoustic emission associated with both. If you look early in time after a slip event, and that's the bottom left-hand signal, part B, it appears to be noise. There seems to be no signal of interest there. If you look close to failure, what you see are classical precursors to failure. So these are impulsive signals that precede failure. They're almost always, or perhaps always, seen in the laboratory, and often seen in Earth, but not always. So with that, let's move forward. So back to what we're trying to do then, we're trying to take that acoustic signal and map through the feature space some fault property. In this case, we want to know what the displacement and shear stress are on the fault. Next, please. So more specifically, you're seeing that continuous wave signal once again on top. The bottom, again, is the shear stress measured on the apparatus. And we're trying to take a snippet of the continuous wave signal and map it to determine whether or not it contains information regarding the shear stress on the fault. So the next slide, please. So here are the training and testing data sets for both the input signal, the seismic signal, continuous seismic signal, and the label, which is the shear stress in this case. The shaded portion in green are the training data, and the gray-blue are the testing data. And what you see on the left are a number of impulses associated with the signal on the right, which is the shear stress. So you can see there are many earthquakes in there, maybe 10 to 15. And with each of those, there's a burst of acoustic emission or seismicity coming from the system. So we train on that region in green, and once the model is built, we ask ourselves, okay, now let's throw away, or let's not allow the model to see the shear stress data. It can only see the seismic data and nothing else. And we ask the model, are you able to predict the instantaneous shear stress on the fault? Next slide, please. The answer is yes, which was truly remarkable for us. And we'll come back to that in a moment. But in the left-hand figure, you're looking at the acoustic amplitude, again, as a function of experimental runtime. And on the right, you're seeing the shear stress data. This is the testing data set now. It's the same data I just showed you in the previous slide, but now we've zoomed in on it. What you're seeing in that box on the left, that blue box, is a mapping from an instantaneous portion of the seismic data to the shear stress. So the blue curve in the right-hand figure are the predictions that the model is making. And the red curve, which is sort of hidden beneath it, it's a dashed red curve, is the ground truth as measured on the apparatus. So we have ground truth. And you can see that the mapping is remarkably good. At any given time, the model can tell us that there is information contained in the seismic signal that maps to the shear stress. And so once the model is trained, if I take some arbitrary portion of the seismic signal and ask, where am I in shear stress space, the model can tell me. Not only that, and next slide. Okay, so I'll come back to the not only that, but I'll explain there's a why to this. What information is there in the seismic signal that can tell us about what's going on inside the fault? It turns out you're looking here at the acoustic emission signal or the seismic signal. Below that are three of the features, the statistical features I mentioned that are used in the model to try to make that mapping. There were 900 statistical features that were used in this exercise, and it turns out about 10 are important to make the mapping, and none others. The three most important are the variance, kurtosis, and thresholds. You can see in this figure that in the top you'll see that burst of acoustic emission. There are 1, 2, 3, 4 bursts. Each of those is associated with a fault slip event. You can see that between each fault slip event, the variance gradually increases with some irregularity. The kurtosis gradually increases, again with some irregularity, as does the threshold. So these three features, plus about 7 others, allowed us to make the mapping that I showed you in the previous figure. So there's no magic here. It's just that the machine learning procedure allowed us to actually discovered the features that were important and showed us what features were important. At which point we can ask, what are the basics? What are the underlying physics that are responsible for this? Next slide, please. So we can also forecast. So this is again the same laboratory data set, and in the top figure you can see again the shear stress signal, and right below that is just a countdown. It's a time to failure. So. And this is a function, again, of experimental runtime. So you're looking at 1, 2, 3, almost 4, 3.5 slip events. And you can see that the clock on the bottom, the red dashed line counts down to 0, which you're not seeing on the axis, but it counts down and then it resets and starts again. So it's simply showing you the time to failure, which is on the y-axis, as a function of experimental runtime on the x-axis. On the bottom, you see that same dashed line and then the prediction. The prediction shows us that the prediction of the time to failure shows us that as soon as we've had a slip event, the system knows when the next slip event is going to take place within seconds. And that blue line tells us that because it follows the red line, counting down to the next slip event. It's not perfect, but it's pretty good. So what it tells us is that there's not only instantaneous information regarding the fault characteristics, but there's future behavior contained in that signal. Next slide, please. So at this point, I wanted to show you that, okay, let's move to Earth. So what? We've done this really interesting exercise in the laboratory. Does it have any bearing on what's going on in Earth? And I want to show you that indeed it does. So let's move to Cascadia. Let's go to the next slide, please, Raj. So some of you may be familiar with the phenomenon of slow slip and tremor in subduction, especially in subduction regions. This was discovered about 20 years ago, and this famous slide is from Rogers and Dragert, published in Science in 2003. On the y-axis, you see the east displacement measured from Global Positioning Systems, GPS, point measurements. And on the bottom, you see the calendar time. The blue dots represent the GPS east displacement at any given time. And what you see there is there's a steady buildup from tectonic loading of the displacement toward the northeast of the subducting slab. That is the Juan de Fuca slab subducting under the North American plate. And then you see that the North American plate lurches back toward the ocean periodically. And that periodicity takes place on about a 12 to 14-month cycle. So that zigzag signal you see represents a number of slip events, and during each slip event, there's a burst of what's known as non-volcanic tremor taking place as well. Now, this is the slowly slipping portion of the slab, and I think that's shown in the next slide, Raj. So sort of shown here. If you look carefully, you see the Juan de Fuca plate subducting beneath the North American plate. You see the locked zone where the megathrust is expected to take place, and the slowly slipping zone down below that. So this slowly slipping zone is, if you're not familiar with it, is exactly that. Slip events take place over about 1 to 2 months. So they're actually the energy released is comparable to a magnitude 9 megathrust event, but it takes place so slowly that we don't feel it at the Earth's surface. The reason we went here is because we have a training and testing data set. In other words, the fact that we have slow slip taking place on a 12 to 14 month cycle, and we have recordings back to the early 90s, means we have a fairly good training and testing data set. So we're not looking at stick slip events here, but slow slip, only because we have enough data to train and test on. Next slide, please. So here's the result. I won't walk you through the details of how we got here, but I'll simply show you that on the y-axis is the displacement rate. I'm showing you rate rather than the actual displacement as measured by GPS. And that's the red signal. On the bottom axis, you see the x-axis, you see calendar time. There's an empty space in there where there were no data. This is for a single station, by the way, GPS and seismic station. So you can see the oscillations in the GPS signal that represent the tectonic loading and then the lurching back of the North American plate back toward the Pacific periodically. And you can see it's quite noisy. The blue line is the prediction from the model after it's been built. And you can see that they match each other quite well. And you can see that the signal, the predicted signal from the model is actually less noisy than the GPS signal. So just to recap, when we apply the same method that we developed in the laboratory to slow slip on Earth, we find that it works, which was a big surprise because I think everybody on the line can appreciate the complexity difference between a simple laboratory fault and a subduction zone in Earth. So, we're looking at a single frictional contact in the laboratory in Earth. The number of frictional contacts is very large. We don't know how large, but very large. And we wouldn't necessarily expect them to behave in the same way, but indeed they do. So next slide, please. So the most important statistical characteristic in this exercise turned out to be an interquantile range, and that is related to the energy of the system, just as the variance is in the laboratory. So I won't describe this, except we'll just move ahead for the sake of time. But I'll simply say that there were a suite of statistical features that were important to make the mapping. The most important was the interquartile or quantile range in this case. We can move ahead. And we can also predict time to failure for the slow slip. So going through the same procedure that I described for the laboratory, if you look at the lower right-hand figure, you see time to failure and calendar date. The red line, the red dashed line is the ground truth from GPS, and the blue is the prediction. So very soon after a slip event takes place, the system points at the time of the next slip event. And that is true for the first three cycles. Then you see it becomes a bit more irregular. And the reason it's irregular is during the training exercise, we didn't see this sort of more erratic behavior we're seeing in the slow slip between 2015 and 17. So again, this is an important point. If your model during training has not seen the behavior it may see in the future, it may fail. It does a reasonable job in here, but it's not perfect, especially in that time frame. So let's go ahead and move on to the next slide, please. So I want to just briefly mention some related efforts that are funded by fossil energy that are taking place at the laboratory and also in collaboration with other laboratories that I'll mention as we go forward. Let's go ahead. So one of the things Ting Chen and her team are doing here at Los Alamos for work in Oklahoma is they've developed a location and a location procedure, not only applying a neural network for identifying events, but also locating events. And this is based on work that came out of Caltech from Zach Ross's team a couple of years ago, where they did the same thing, developing a neural network for Southern California to create a catalog, a new, more robust catalog, and also to be able to locate those events. The advantage is that, number one, you can identify, once you've trained a model, you can identify many, many more events, but also you can locate them automatically once you've trained a second model for location. And so the training in this case were multi-stations, 11 transportable array stations. This was a U.S. array some of you are familiar with that marched across the country a number of years ago. Went through Oklahoma and captured quite a bit of the seismic activity between about 2008 or 9 and 2012 or 13, I believe. And so that's the that's the data that were used, and the locations are from the Oklahoma Geological Survey catalog. Next slide, please. So when Ting applies this approach, she's able to not only identify many, many more events, 150 times more events compared with the OGS catalog, but locating 8 times as many events in the OGS catalog. So, this is another great example of how powerful these tools are, and once you've created the model, they're fully automatic and they're very fast. Often you can't generalize to other areas. So if Ting trains this model in Oklahoma, it's not going to work in Arkansas. You have to retrain the model for a geographic region, and that's been shown a couple times now by various groups, including ours. But once you've trained for a specific region, this is a very powerful approach to tease out more information in regards to earthquakes and also locations. Next slide, please. So then I wanted to just mention work by Yuzuo Lin and his team. This is one of the things Yuzuo and his team are working on is new ways to image, and in this case, applying a neural network to image. And the way this works is you train a 2D model on many, many different layered structures and geometric structures that include faults, etc., faults, folds, etc. You do this maybe 10 to the 6 times, so you have a very large training data set. Once you've built the model, and in this case it's a convolutional neural network, you can apply it to the Earth, and or you can apply it to test data sets like Kimberlina, and that's what you're seeing here on the right. So the ground truth from Kimberlina is that upper cross section, and in the center is the traditional approach using standard tomography approaches, and the data-driven approach here that Yuzuo has developed shows the result, which is actually very clean. So this is an example of how it works on a testing data set like Kimberlina. If you apply it to Earth, they've had significant success as well applying the trained model to Earth. Next, please. So another thing I wanted to mention was something our team has been working on We're really interested in Earth deformation for a lot of fossil energy applications, geothermal, CO2, etc., inflation, deflation, fault slip that might manifest itself on the Earth's surface. Currently, we use GPS, but we wanted to move to INSAR because INSAR gives you an aerial snapshot of the difference in deformation over some period of time. So it's a far more robust measurement. The problem is with INSAR, and some of you may be familiar with this, is that it's extremely noisy due to atmospheric disturbance and also topography. Bertrand Ray-Leduc, an individual on our team, has developed a neural network approach, convolutional neural network in this case, to denoise INSAR and also to unwrap the phase. And that is working extremely well. We've got about an order of magnitude better displacement resolution from that procedure than we had from an expert, which is pretty remarkable. Plus, it's super fast. So that work is ongoing, but that will be incorporated into a number of projects that you've seen today, earthquake projects, including Ting's work, our work, and a stress model that you're about to see as well. Next slide, please. So the stress model is actually right here. This is work in collaboration with Monica Macera at ORNL and our team at Los Alamos. And basically the idea is to use a joint inversion to get the elasticity, and then you calculate the strain field using gravitational load, and you back out the stress. That's sort of the simple version on how this is done. This has been applied successfully to Oklahoma, and there's a paper in review describing this at present. But it's a way to back out the stress field. And we want to, obviously, we want to be able to use that in various environments, and those include CO2, geothermal, and oil and gas. We want to be able to characterize the evolving stress field and know where we have change due to fluid injection, to fault slip, etc. Next slide. Oh yeah, excuse me. Hang on. Please go back, Raj. And so we're incorporating in INSAR into this as an additional constraint. That work is just taking place right now. Next slide, please. And the only other thing I'll say is eventually that stress model will be a neural network. So we won't go through this entire procedure I just described, but we'll use a neural network trained model in lieu of that and apply it to real data. The next thing I wanted to just briefly mention is fluid-induced fracture. This is work that was done first by Yves Guglielmi and his colleagues. Yves currently at Lawrence Berkeley Laboratory. He and his colleagues in southern France have done a number of experiments where they go out, they drill through an inactive fault, they place packers on either side of that fault, they inflate and make it slip. They measure with a strain meter in the fault plane itself, strains, 3 components of strain. They also measure seismicity. They measure fluid volume and permeability. Well, they can back out permeability, and they measure fluid flow. I won't go into the details of what you're seeing in that bottom plot. The data that we've been analyzing are from this site in southern France. Next slide, please. And I'll simply say that it turns out that it looks like fluid injection faults behave like a tectonic fault does and a laboratory fault, which is to say we can, if you look at the bottom part of this figure, you see the shear strain as a function of time. For the actual measured displacement, shear strain as measured by Yves and his colleagues, the red dashed line, and the instantaneous predicted values from the model. So we're honing this result right now, but it looks like it's working reasonably well and leads us to believe that we can do just as well with fluid-induced fracture as we can for tectonic fractures. And obviously that's of great importance for a lot of the work many of us are doing currently, both here at Los Alamos and for all those of you at other institutions who are listening in. Next slide, please. I'll say that it looks like we can also determine the instantaneous permeability This is quite new, and I won't say more because we're still trying to convince ourselves this is real. But the measured permeability as a function of time is the red dashed line, and the blue is the predicted. So it appears that the seismic data that we're measuring contains information also about the permeability state. But take that with a note of caution because we're not 100% convinced. We are not yet convinced that this is a real result or a result we can trust yet. Next slide, please. So I'll just mention that there's another effort going on here and with collaborators elsewhere, led by Jonathan McCarthy here at Los Alamos regarding cloud computing. If you look at that the yellow text, traditionally, the download and store process analysis is about 6.5 megabytes a second. Next slide, please. If you calculate on the cloud and stream data from some data center like IRIS, which is a data center for seismic data, you can get a terrific speed up to about 100 megabytes per second. But if you move everything to the cloud, next slide, please. What Jonathan has seen is about 2.5 gigabytes a second with calculation and data in the cloud. So you're doing everything in the cloud. The data live in the cloud, the processing lives in the cloud, and then you download the result. So next slide, please. So last thing I just want to bring up that a number of us here, and there are many other individuals involved in this, both at Los Alamos, at Livermore, and elsewhere, ultimately. But one of the things we're looking at is to look at visualization for our purposes, specifically for state of stress. But obviously, this would have applications to other problems. And this is in its infancy. Clearly, there's a smart effort on visualization. And we will be tying into that effort on visualization as we move forward with our nascent effort on this. I won't say more because there isn't much more. Next slide, please. So just a final few slides here. People worry that computers will get too smart and take over the world, but the real problem is they're too stupid and they've already taken over the world. I love this quote from Pedro Domingo's book on the master algorithm because it's so true. There's this concern about the future and computers becoming too smarter than humans, et cetera, but we already suffer from computers now. When you call the doctor's office and you can't speak to an individual, you call Amazon and you can't speak to an individual. It's maddening. So in that sense, we're already there. Next slide, please. And I just wanted to briefly mention this, too. This is the hype cycle for artificial intelligence as of 2019. This is from Gartner, who puts this out once a year. And this is just amusing because I think where we currently are in geoscience is near this peak, the peak of inflated expectations about this new toolbox and what it can do for us. Ultimately, we're going to have a crash to the trough of disillusionment. We're going to slowly have a slope of enlightenment and then a plateau of productivity. In some cases, with some of the techniques in the large machine learning toolbox, we're at the plateau of productivity. But for many techniques, we're still at the peak of inflated expectations. And so I think we can expect this trough of disillusionments for certain techniques and failures of certain techniques, but ultimately we'll sort through that and we'll get to a point where we're much more productive using these machine learning methods than we are today. Next slide, please. So some of you may have been aware of a meeting we were hosting next week in Santa Fe, and this was organized by a number of us at Los Alamos with colleagues from Stanford and elsewhere, Rice University. We've had to delay it because of Corona, and that will be announced soon. If you're interested in getting on the mail list, please send me an email and I'll put you on the mail list. We anticipate that the meeting will be held probably next fall. Next slide, please. And just a last thing, self-promotion for a group of us that wrote a review paper on machine learning in geoscience. This is Carrie Ann Bergen, who was a student of Greg Barroza at Stanford, myself, Martin de Hoop at Rice, and Greg. This paper came out last spring, summer. So if you're interested in kind of getting an overview of the state of the art as of 10 months ago, please take a look. Next slide, please. So the take-home message here is the vignette I showed today, the vignette from the laboratory on Earth, point to the fact that the noise is the signal giving insight into fault physics, and machine learning tools revealed it. These signals we had discarded as noise previously. We'd studied them in detail, but we had not seen that they contained important information regarding the physics of the system. Thanks so much for your attention.
Thank you so much, Paul. I'd like to open it up now for questions, if anyone has any questions. We have the lines unmuted.
Yeah.
Okay. Okay, does anyone have any questions for Paul?
Hi, Paul. This is Ahmed Ibanna from University of Illinois.
Yeah.
Amazing presentation, as usual. And I wouldn't ask about the technical content, but since you probed some philosophical aspects for machine learning, I would like to ask you about this observation that some of our laws of physics that we take to the heart are actually data-driven, right? Like for example, F equals ma is purely data-driven from observations of planetary motion and stuff like this. However, it's very generalizable. So it can be applied to a broad range of phenomena beyond what the data that driven it has shown. So what do you think is the limitation for neural network approaches, which are also data-driven? What makes them very limited in their generalization ability? What are we missing? Is it because we are just assuming so many parameters in the training algorithm, or what? I'm curious to know what you think about this problem.
So let me just make sure I understand, Hamed, your question. You're wondering about generalization. So you train a model, and then it won't generalize to another geographic region, for example, in the case of earthquake locations, as I described from Ting, or something like that. Is that what you mean?
Exactly. While we have like physics laws like F equals ma, they are also data-driven because they are based on observations of celestial objects, but we can apply to many different other physical systems.
So I think F equals ma is a fundamental law of nature. And I think what we're seeing here for a lot of geoscience applications is that they're localized. The Earth is not necessarily homogeneous and responds in the same way everywhere we look. And I think that's easy to understand at some level because we have very different rock types and different tectonics as we traverse across the Earth. So I think as a result of that, what we're seeing, at least at present, in this early stage of applying these tools to our problems, is that these local or regional influences won't generalize to other regions. In some cases they do, and in some cases they don't. And I think we'll have a much better picture of this in say 5 years as time goes by and more of us start applying these tools. But I do think that this is an important aspect, is the regional differences and the local differences in geology.
Thanks, Paul.
Paul, if I could follow up on that question in your response, would you say that the same approaches that you're talking about you think we can apply the same approaches to different geologies, local and regional, and as you're saying, kind of learn from that so that we can tease out what things are more universal and what things are more geology dependent?
Yeah, and I think the initial approach is you see if it will generalize. So you train a model in one locality and you see if it will generalize elsewhere. And if it won't, then you develop a new model. And what we're seeing is that for some problems, generalization actually is clear-cut and it works. But for other problems, generalization doesn't work at all. So, for example, what Yizhu Lin is showing with this tomography CNN that he's developed is that it generalizes. He can train it on synthetic data, and it generalizes to it appears to generalize to all types of geology and structural systems. This is also true of the INSAR model that my colleague Bertrand Ray-Leduc has developed, where you can train the model on synthetic data and apply it broadly. So this is the case where you're training on synthetics, and so generalization is more clear-cut. But if you're training locally, for example, what Ting Chen did, and this is also what Zach Ross did from Zach's at Caltech, where they're trying to develop earthquake catalogs applying neural networks and also locate sources applying a second neural network, that really depends on the local geology and the elasticity. And as a result, if you try to take a model trained in Southern California, and Zach did this, and apply it elsewhere, like Japan, it didn't work. If Ting hasn't done this yet, but if Ting takes her trained model in Oklahoma and takes it to California, it's going to fail, almost certainly. And it's because the geology is so different.
Hey, Paul.
This is Xue from ERC. I have a question about how can we use machine learning to deal with time series data. So normally when we develop a machine learning model, we split data randomly into a training set and testing set. But for time series data, they have time series trait, like there is autocorrelations among the data points. If we split them randomly, we assume that those data points are randomly, there's no connection.
Right.
So how do you do with the time series data?
So okay, let me make sure I understand the question. A lot of us deal with seismic signals or acoustic signals, and that's, I think, your point. And these are a time sequence. And so how do we deal with these, especially in regard to something like a neural network? Is that your question?
Generally, just so any signals with a time trait. So basically, if there might be autocorrelations for the data by time, and if we split data randomly, we assume that there's no connection among them, but this might not be true.
Right. So if I understand your question, and let me try to repeat it. So you have a time series, and if you mix up that time series and take sort of arbitrary points out of it, are you asking whether or not there's a relationship between one data point, t equals 0 and t equals 10, for example?
Yeah.
So, right. I mean, I don't know the answer to that question at the moment. It's not obvious to me, except to say that in a sequence of time series, if you have two portions of the data set, as we did in the laboratory and in Cascadia, where you have a training and testing data set that are separate, then it's clear cut. If you don't have much data and you're required to train on portions of the same data set you would test on, one has to be very careful that you're not spoofing the model. And I think that's what you're getting at. Is that right?
It is right that if I use same data set and I treat it as a regular data set and it works pretty good for the training and testing set. But when I apply the model obtained from this data set to a new time series, it may or may not work.
Oh, I see. So it's again the question of generalization to another data set. Yeah, right. So I think this is another issue that we don't really know the answer to yet. Whether or not whatever model we develop for whatever purpose will generalize. So, I think, again, time will tell. So I wish I had a better answer for you, but I'm sorry that I don't.
That's okay. I have another question about your signals about the seismic. So there are a lot of, when you do a machine learning to to a seismic signal, should we remove the noise to apply the model, or just use the raw data set?
You know, this is where the black art comes in applying these tools. There's pre-processing, and then there's the sort of the post-processing, which is the tuning of the model. And this is a really important point, that you don't just take a model, apply it, get a result, and believe it. You really have to iterate and tune. And part of that tuning requires, okay, let's start with not filtering the data at all. Let's just see what happens. Okay, it doesn't work. Let's filter the data and see what happens. Does it work? Well, it works better. But now we have to tune the model itself after we pre-process the data and things improved, to see how we can improve it by tuning the model. And that tuning procedure, which you may be familiar with, is changing the hyperparameter space, changing the feature space, and so you're probably aware of that. So I think it's just a really important point that you get an answer with any of these machine learning tools. It isn't necessarily. You may see nothing, but it doesn't mean that there's not something there. One has to keep trying. And I think that brings up a really important point, and that is that those of us in geoscience, as we get into this, it's really useful. In fact, I think it's critical to work with experts who really know machine learning. That's how we started, and that's how we continue to work. We have, domain experts. As all of us listening in are domain experts in one aspect of geoscience or another. If we team up with somebody that really knows machine learning, we can really progress. If we try to do it ourselves, yes, we can make progress, but we can also make a lot of mistakes, and we're seeing that in the literature, that people are making mistakes and publishing it. So get off my soapbox.
Yeah, thanks.
Thank you.
So Paul, last question really quick. So you mentioned actually for the Oklahoma State earthquake evidence over there, do you continue to work with geological survey over there? Because the image you show of the really strong, maybe really high magnitude over there. So I'm kind of curious how about the weak evidence over there, how your model can catch up, or how much sensitive over there, strong versus weak evidence. Okay.
So sorry to interrupt. You weren't done, but you're asking about Oklahoma and relationship to geology in part, and the results I showed from Oklahoma by Ting Chang. Could I ask you it would be best if I could refer you to Ting, because she's the expert in this area. She's been developing this work, and I think it wouldn't be appropriate for me to answer the question. So if you would like her email address, please write me, and I'm happy to give it to you if you can't find it. But it's Ting Chen, Chen, at Los Alamos.
Okay, thank you.
You're welcome.
Yes, Paul, hey, this is Salanga Mahapatra from headquarters.
Hello.
Hey, I have a couple of questions, because I did the machine learning and neural network in the past for the well production data, reservoir data, but what would be the ideal proportion of testing data versus trained data sets?
I'm sorry, it was a little muffled. If you wouldn't mind repeating your question, I'd appreciate it.
Yes, generally we take 60 or 80% of data for training purpose.
Yep.
The rest we keep for testing purpose.
Right.
So for your Cascadia modeling, what was the percentage?
What was the split?
Uh-huh.
Okay, so the question then is, what portion of the data do you use for training and what portion do you use for testing? In Cascadia, we used about 70% of the seismic and GPS data for training and about 30% for testing. And that one of the hyperparameter studies was to see what happens when you decrease the amount of training data. But in any case, frequently, I think to answer your question, frequently what we find is the bulk of the data you use for training and then some smaller portion for testing, and that's what seems to work best for at least the problems that I'm familiar with. Does that answer your question?
Yes, sir. My second question is regarding the time series question that somebody asked you. I mean, you mentioned that it is a closed time-space analysis, correct?
I'm sorry, could you repeat that, please?
It's a definitive time-space, say from September to October or October to November. It's a closed time-space analysis.
Correct.
Okay, so how do you handle any extra signals that may crop up? I mean,
again, I'm sorry. I couldn't quite follow the question. Could you please repeat?
No, the one thing you consider the GPS, which is okay, and the other thing you consider the stress measurement. Stress measurement may be continuous, may be discontinuous, correct?
Correct.
So how do we handle that?
How do you handle discontinuous data? Is that specifically what you're interested in?
Yes.
Yeah, I mean that's an interesting question, and I think it's really application specific, at least in my experience with this. One could say that, for example, with seismic data, you have a very high data rate. GPS has a low data rate in general, and INSAR even lower. Every 6 days with Sentinel-2, and those are still continuous, but the data rates are very, very different. And maybe that's what you're getting at. Are you asking when you have a problem where the input data has a very different data rate or sampling than the label?
Yes, I mean it's like when we do the seismic inversion, taking the well data. I mean, they both have in different scale of resolution.
Right. So for situations like that, we do averaging of the. So the example I just described, where you with INSAR, for example, where you have a 6-day repeat time on the satellite, so your sampling rate is every 6 days, in contrast to seismic data, which is a very high sampling rate. So what we do is average over a 6-day or maybe up to 50 days or something like that of the seismic data to make one prediction of the average of the INSAR time series over that same 50 days, which is 8 data points, in contrast to the millions and millions of data points you have with the seismic signal. So it's a question of averaging over windows that are appropriate for the input data and the label. Does that make sense to you?
Yes, very much. My last question is, I mean, we have developed microseismicity for reservoir characterization. So whether this application can be transported to microseismic level for better fracture characterization?
I apologize again that I couldn't quite hear because of background noise. Would you mind repeating one more time, please?
Yes, I was inquiring whether this method can be further applied to characterizing fracture network in the hydraulic fracture sites.
So there are individuals working on that very problem. Our team isn't necessarily looking at fracture systems. I mean, for example, Hari Viswanathan's team here at Los Alamos and with collaborators elsewhere are looking at that problem. But I think the short answer is yes. And then specifically, I think that's something that we should have as a discussion about exactly what you'd want to know. And maybe that's a good discussion to have offline with Hari and myself.
Okay, thank you.
Thank you. I guess, well, since there seem to be no other questions, thanks so much for your time. I hope this was useful for some of you, or maybe even all of you. And take care, all of you. And good luck with the corona, all of us.
Thanks, Paul. I'm not sure if you had to fill on.
Thanks.
Thank you.
Thank you.